This is the first lesson in Chapter 6 for Algebra 2. It's on graphing systems of equations. Before we start the actual lesson, I just kind of want to refresh your memory about a couple of things with equations and solutions and what they are. So first of all, what is a solution to an equation? It's a coordinate that makes the equation true. For example, the coordinate, let me think, 1, -4 would be a solution to this equation because if I put in y equals -4, I need to ask, is that equal to 5 times x is 1 minus 9? Well, 5 times 1 is 5. 5 minus 9 is -4. So since this is true, that means that this is a solution to the equation. Again, it's a coordinate that makes it true. The second thing is, what is a system of equations? A system means kind of like more than one thing. So it's more than one equation. And then what is a solution to a system of equations? It's kind of a hybrid of these first two things. It's a coordinate that makes both or all equations true. So when we talk about looking for a solution to a system of equations, we're looking for a unique coordinate that makes true statements out of both equations involved. A couple places that I've had to use these was my first year teaching when I was supervising 7th grade concessions, when I was doing a fundraiser selling shirts and pasta, and then figuring out how much my student loans were going to be for the next semester, how much to take out for them. If you want to ask me questions about how that worked, I can explain them. So there are a couple types of systems. A solution to a system, again, is a coordinate that makes both equations true. And it's a coordinate on the graph of both lines. So if you have a graph, you're looking for basically the place that they cross. So there's one scenario where maybe you have one line looks like that, and the other is like this. So that would be your one solution, -1, 1, 2, 3, 4, 5, 6. That would be your only place that they share a coordinate. The other option might be, okay, you've got this blue line, but maybe you have this one running next to it. If they're parallel, there's no solutions. There's no solution. The first scenario, there was one solution. The last one is, if you have that blue line there, and then you put another red line right over it, they basically make one purple line, right? They're right on top of each other, so they're the same line. Those would have infinite solutions. So there's only 3 possibilities. They cross once, they never cross, or they cross all the time. There's different names for those, but I'll address them in the notes. So in this, what we're asked to do is graph the following system of equations, mark the coordinate of their solution if it exists, and write it on the line. Then we want to write the type of system. So I'll give you the different names in these examples. So this one I'll do in red, and this one I'll do in blue. So for red, our y-intercept is 2, so we're going to go up to 2. And our slope is 1/4. Now you have to be careful because this box is a step of 2. So technically 1 is halfway right here. So rise 1, run 4. Rise 1, run 4, or drop 1, back 4, drop 1, back 4. So this is our red equation. And then in blue, we've got a y-intercept of 11. So 11 is right here. And a slope of -2. So we're going to drop 2 and go forward 1. Drop 2, go forward 1. drop 2, forward 1, drop 2, forward 1. That is where they cross. So the solution there is 4, 3. The coordinate is 4, 3. That's the solution. Now, when they cross once like this, when they make one intersecting coordinate, this is called a consistent independent system. They're consistent independent. Okay? If it crosses once, that's what it's called. All right, next one. I'm going to use this one. It's going to be purple. This one I will do in orange. So in purple, our y-intercept is 7, and our slope is -2. So we're going to drop 2, run 1. Drop 2, run 1. Drop 2, run 1. Now, in orange, the problem here is we have this 3. We can't have this 3 here. So what we're going to do is divide by 3 on both sides. So chunga chunga, y equals -2x plus 7. You might notice we have the same equation. 7, drop 2, run 1, drop 2, run 1, drop 2, run 1. So it's going to be the same line. What we'll say for coordinate is infinite solutions, because we can't just list all of them. They go on forever. These ones are called consistent dependent, because they depend on each other. Like how many solutions you have depends. Is it the same as the other equation? That's kind of what I think. So they're consistent dependent when they're exactly the same. If you're the same as someone, you depend on them. And then this one, I'll do this in red, this in blue. So in red, our intercept is 1, our slope is 5. Drop 5, 1, 2, 3, 4, 5, run 1. Or up 5, 1, 2, 3, 4, 5, back 1. Now in blue, we've got an intercept of 1, slope of 3, so rise 3, run 1, rise, oops, we're out. Drop 3, back 1, drop 3, back 1. This is our one solution. The coordinate is 0, 1. And these are consistent independent. They are not exactly the same, so they're independent. All right, this one I will do in black. This one I will do in blue. So in black, our intercept is 1 and our slope is 4. 1, 2, 3, 4, run 1. 1, 2, 3, 4, back 1. And then in blue, our intercept is -3. 1, 2, 3, 4, run 1. 1, 2, 3, 4, run 1. Or 1, 2, 3, 4, back 1. All right. This one has no solution. Because they're running parallel, they're never going to cross. So there's no solution. These are called independent. Sorry. Inconsistent. Sorry. Inconsistent. So if they're parallel, they are called inconsistent. You have an assignment. It's 3.6, 3.7 graph worksheet. It says 3.6, 3.7 on the top.